Welcome to our final video in the process of differentiating transcendental functions. This video will demonstrate or introduce you to a process called logarithmic differentiation. Now, this is a process that can be used in one of two situations. One of the situations where you would use it is optional, and the other one is compulsory. It's the only way to get the derivative of that type of situation. So the first one I'll start with will be finding the derivative of what we would refer to as, for lack of a fancy mathematical term, a messy product or quotient. Well, I think if you were to look at this with me, you would agree this is a messy product and quotient. So imagine if I said to you, find the derivative of this. I believe we could, but the issue would be it's a quotient. So in that quotient rule, when I did derivative of the numerator, it would be a triple product. So I'd have to do derivative of the first times the other two, derivative of the second times the other two, and so on and so forth. When I took the derivative of each of these ones, they're all chain rules as well. So I think this certainly would meet the bill of a messy product and quotient. Well, we could turn this into probably what you might agree with me at the end of the process is an actually much easier derivative to do. It's still going to take up a fair bit of space in our notebooks, but I think you would agree it's probably going to be an easier way to do this. And the way I could do it is to use laws of logarithms to turn this mess of things multiplied and divided into addition and subtraction instead. Now, you may say, well, how are you going to do that? I shall show you. What we're going to do is we're going to use a process that you would have run into before, where let's say you had something like this. I don't know if you can remember back in pre-calc 12a. Let's say you had 3 to the x equals 7 to the x plus 1. Well, you can't get these both to be a common base, so the strategy we used in that situation was to take the natural log of both sides of the equation. Natural log of 7 to the x plus 1. And then you would use your laws of logarithms and bring your exponent to the front, x natural log of 3, x plus 1, natural log of 7, and then all of a sudden an exponential equation gets turned into a linear equation, where you rearrange, collect your x's on one side, numbers on the other, and away you go. We're essentially going to use that exact same strategy to turn this into a bunch of things added and subtracted, and I shall show you how that works. So we're going to take the natural log of the left side and the natural log of the right side. I gotta write this all out again. So it's x squared minus 1 to the 5th radical 2x plus 9, 5x cubed to the 8th over 10x minus 1, and 5 minus x to the 7th. So I've taken the natural log of both sides. Now at this point, as I mentioned earlier, we assume students have mastered their laws and properties of logarithms. And I know that's not necessarily always the case, but unfortunately that's the assumption you've got to work under, that you do know all these laws and properties. So what I'm going to do is leave the right side as it is. I'm going to expand this all out. I'm going to use all my laws of logarithms at the same time. So laws of logarithms said that if you have things that are multiplied together, you can write them as products. So, and then things that are divided, you can write them as quotients. Now, this is going to be natural log of x squared minus 1 to the 5th plus natural log 2x plus 9 to the 1/2 plus, again, that's plus because they're multiplied together, natural log 5x cubed plus 2 to the 8th. Now, these ones are quotients, so they're divided by, so then it's going to be subtract natural log 10x minus 1, and then subtract, oh, this one should have had a half on it because it was square root, subtract natural log 5 minus x to the 7th to the 1/2. Now, I didn't want to do too much at once this first example, but if this was me doing this question, that's my product and quotient laws done. I would have also done the power law at the same time, because now what I'm going to have to do is rewrite this all again, and I'm going to bring all these exponents out to the front as coefficients, which the power law says we could do. So natural log of y is equal to 5 natural log x squared minus 1 plus 1/2 natural log 2x plus 9 plus 8 natural log 5x cubed plus 7. That's 7? 2, I guess it is. Can't make up my own writing. So 2. No exponent on this one, so it just stays natural log 10x subtract 1. There is an exponent on this one of 1/2 natural log 5 minus x to the 7th. Now, unfortunately, what will happen from time to time is a student may get all of this done down to here, which indicates they have a good grasp of logarithms, and then they're quite proud of themselves and they go on to the next question. Well, our goal was to find the derivative of this, which I have not done yet. All I've done is changed it from a messy product and quotient into a bunch of things added and subtracted. So what I now have to do is take the derivative of this. Now, watch how it's going to be so much easier. So the left side, it's going to have to be implicit, so it's 1 over y. Natural log of u is 1 over u du equals, because these are constants, you just write the constant, and now it's just going to be du over u, what is it, 5 times. So du over u, easy. 1/2, constant stays in front, du over u, so 2 over 2x plus 9, plus 8, du over u, 15x squared over 5x cubed plus 7, minus du over u, minus 1/2 du over u, so negative 7x to the 6th over 5 minus x to the 7th. So yeah, this did take up a fair bit of space, but this was so much easier because I did not get into those product rules and quotient rules and chain rules. It was simply du over u 5 times. Now, I'm not quite done yet. Again, this is more time-consuming than it is anything else. I need to get dy dx by itself, so I have to multiply both sides by y. So if I multiply by y here, that'll get rid of that. Oops. So then, dy dx, remember, whatever you do to one side, you need to do the same thing to the other side. And as has happened before, you cannot start out with an explicit function, all x's on one side, and then your derivative end up with a y in it. So, this is the painful part right here. My derivative is going to be all of this. Now, you can tidy things up a little bit as you go if you want. So 5 times 2, I could say that this is 10x over x squared minus 1. This 2 will get rid of this 2. And it's 1 over 2x plus 9. 15 times 8 is 120 x squared over 5x cubed plus 7. Subtract 10 over 10x minus 1. Not much to tidy up here. I could go minus minus and say it's really a plus. 7x to the 6th, 2 onto 5 minus x to the 7th. X to the 7th. Now I'm going to put a big square bracket around all of this. And instead of multiplying by y, we are going to replace y with what y is equal to. But unfortunately, y is this big mess right here. So then I would need to rewrite that all in here instead of the letter y. Now I'm going to cheat a little bit here. Get my eraser out. Unfortunately, you're probably not going to be able to do this on a test, but I'm just going to take out the good old clipper here, and we'll save me some writing. So there's my y. I'll add that to the clipboard. It should be there now, actually. Scroll down. It should be giving me the option to paste here. There we go. Paste that in there. Size it down so it'll fit. And there you go. But again, you'll have to write that out by hand. I'm just playing around with a little bit of the technology that I have available. So instead of y, I replaced y with what it was equal to. And there would be my derivative. Now you can imagine if we had done that using all those multiple chain rules and product rules and quotient rules that I had mentioned, it would look nothing like this answer, which is a good example to show you that often your answer can look very different, but still also be correct. Let's try maybe one more of those. So here's one that has, let me see here. So I'm going to take the log. This time I'm going to kind of be a little bit more concise with it. So I'm going to take the log of both sides, natural log of all this. Now I'm going to use my laws of logarithms. So it'll be the natural log of y. And now I'm going to bring my exponents to the front at the same time. So 6 natural log 3 minus 2x to the 5th, right? It would have been to the 6th, but I brought it to the front. Plus natural log x to the 5th minus 1. Subtract 8 natural log 2x plus 7. Subtract 4 natural log x to the negative 5 plus 2. Take the derivative, so 1 over y dy dx. Now it's 6 du over u, so negative 10x to the 4th over 3 minus 2x to the 5th plus du 5x to the 4th x to the 5th minus 1 minus 8 2 over 2x plus 7. Subtract 4, negative 5x to the negative 6 over x to the negative 5 plus 2. Now to get dy dx, I would have to multiply both sides by y. Right, that would get rid of that for me here. That would mean I'd have to put this whole right side in brackets times the letter y. And where's my, oops, here. This is my y. And then I'll come down here. Beauty of technology. Why is that not giving me the option to paste? Could have wrote it out by now. Let's see here. Insert. Edit. Paste. There. Like I said, it would have been quicker to write it out by hand. Anyway, that would go there in a bracket multiplied. That's your y. And this is a process, as I said earlier, called logarithmic differentiation. Neat little process to have at your disposal. Now, don't get carried away. Make sure you understand when it can be used. This has to be products and quotients. As soon as you put addition or subtraction in between these, this would be a useless process. Now, the other situation where you have to use this, I did allude to it in one of our earlier videos, is when you've got a base raised to an exponent where the base is not a number. So we have a rule for the derivative of b to the u, which is b to the u ln of b times du. But that is for b being a number. B's not a number here, so that rule doesn't work. We have a rule for the derivative of x to a number, which is the number times the exponent, and we take one off. Unfortunately, this is not one of these. Therefore, these rules cannot be used. Unfortunately, year after year after year, students try and use one of these rules to differentiate this situation. It will not work. So what you need to do is take the log of both sides, just like we did on that last one. So this one is not optional. You have to do it this way, or else you are not going to get the correct derivative. So let's take x to the x to the fifth. So I take the natural log of the left side, the natural log of the right side. And again, the reason I'm doing it is because base and exponent are both functions. Then you have to use this strategy. It will not come out in the question and say use logarithmic differentiation to differentiate the following. You need to be able to recognize this is the situation. Now, when you do this, it's important that you do your next line where you bring the exponent to the front. And that fixes your problem. You no longer have an exponent base raised to an exponent. But what you do end up with, though, every time here is a product. So you have to now make sure you use the product rule. So the derivative of the left side would be 1 over y dy dx. Product rule, derivative of the first multiplied by the second, plus the first multiplied by the derivative of the second, which is ln of u, 1 over u times du. Derivative of x is just 1. Like before, get the y by the dy dx by itself, so I've got to get rid of the y. Get rid of the y. Well, one good thing is it's not nearly as painful to write out because your y equals here are usually not very complicated. Here would be your final answer then. Dy dx would equal 5x to the fifth ln of x. X to the fifth over x is just x to the fourth. If you want to tidy that up. And now instead of y, this is what y equals. X to the fifth. And there you have it. Logarithmic differentiation to take the derivative of an exponential situation where the base and the exponent are both functions. Okay, I got one more for you. So base is, this one's real, that's a function, and that's a function. So base and exponent, both functions. Take the natural log of both sides. Ln of y equals the ln of the natural log of x to the fifth to the exponent cos x. Bring your exponent to the front. Product law of logarithms. Take the derivative now, both sides, so 1 over y, dy dx. Remember, product rule here. Cos x, the derivative is negative sine x. There's derivative of the first. Multiply that by the second. Plus the first. Now I need the derivative of ln u. So the derivative of ln of u is 1 over u. And now I need the derivative of this, which would be du over u. Close that off. So I need to isolate and get y by itself. Right there. This whole side needs to get multiplied by y as well. Y, if you forget now, whoops. Y is that expression up top. Okay, so my derivative, dy dx, would be negative sine x, natural log of the natural log of x to the fifth, plus cos x. Let's just clean this up a little bit here. I've got to have a 5 left there. x to the fourth over x to the fifth is going to give me an x in the bottom. So x natural log x to the fifth. And now you multiply by y. And y was the natural log of x to the fifth raised to the exponent cos x. Now remember, where you get that is from your original. Right? Y equals this. Now students will always say, do I have to do that simplifying that you did in here when you were writing it out? And the answer is no. But if you look at an answer key and you have this and you see this, hopefully you'll be able to look at it and say, oh, okay, I see they just tidied that up a little bit. I didn't do that, but hey, we're both correct. All right, so that shows you how to do the process known as logarithmic differentiation. So it's really important in this one that you can pick out when to use this. And the key here is, as I said in the first example, your base and the exponent are both functions. All right, thanks for watching. That does wrap up all of our information we're going to do on the derivatives of transcendentals and using transcendentals for differentiation purposes. If you have any questions, make sure you reach out. Best of luck with your practice questions.